All right, welcome everyone. We'll go ahead and get started. I'm pleased to present Xuanyu Chen. Xuanyu is a research scientist at CIRES, affiliated with CU Boulder, and the NOAA Physical Sciences Laboratory, just up the hill here in Boulder. She got her BS in marine science from Ocean University of China in 2015 and a PhD from the University of Rhode Island in 2020. She's a physical oceanographer by training, but her research interest has always been in air-sea interactions and in understanding the ocean's imprints on the atmospheric boundary layer. In Rhode Island, Xuanyu investigated how shoaling ocean surface waves modulate air-sea momentum flux in coastal waters during landfall and hurricanes and subsequent impacts on storm surge using numerical models. She pivoted to study the interaction between mesoscale ocean temperature anomalies and trade wind cumulus as a CIRES postdoc in 2021 and has been investigating this topic since then with scientists at CIRES and NOAA PSL using both observations and large eddy simulations. All right, I'll turn it over to you.
Yeah, thank you, Hugh, for the warm introduction. And thanks for this great opportunity for me to present this work here to this audience at NCAR, who has a lot of expertise in clouds and large eddy simulations. So today I will be talking about mesoscale sea surface temperature, warm anomalies, excite trade cumulus generation in North Atlantic trade using both satellite observations and large eddy simulations. And I work with a group of fantastic scientists listed here. And we want to acknowledge funding from NOAA Climate Program Office, NOAA Cooperative Agreement, and also support from NOAA PSL. So to start off, why do we want to study the trade cumulus, these puffy-looking clouds here? Because they are one of the most prevalent cloud types on the planet. And they play a net cooling effect on the Earth's energy budget by reflecting more incoming solar radiation back to the space than trapping the outgoing long-wave radiation. And how these low-level clouds respond to a warmer climate is a leading source of uncertainties for climate projections or climate sensitivity estimates. So showing here on the left is the paper by Myers et al. 2021, who estimated the marine low cloud feedbacks using using satellite observations, which are the results of which are shown in blue. So here he shows that the climate models showing orange markers, the climate models overestimate the cloud feedbacks from trade cumulus. This basically means that the cloud amount of the trade cumulus is predicted to reduce in response to a doubling CO2 and a warmer global SST. So basically this will reduce the net cooling effects and become a positive feedback, reinforcing the warming in climate models. But then in observations, this feedback is neutral, near zero. So basically means that the trade cumulus cloud amount is quite resilient to global warming. So Ville et al. 2017 has a review paper. They summarize that these trade wind cloud feedbacks appear to depend on two important aspects. One is how the cloudiness near cloud base is controlled by interplay between turbulent, convective, and radiative processes. And then second is how these different processes interact with their surrounding environment, and then influenced by the mesoscale cloud organization, which is a topic with a lot of recent enthusiasm because Beyond Stevens et al. Have shown that there are four archetypes of atmospheric mesoscale cloud organization in the Northwest Atlantic trade wind boundary layer. And then they name these different patterns nicely as sugar, gravel, flowers, and fish. This organization patterns span from 2 kilometers all the way to 2,000 kilometers. And the study have also shown that these different organization states in the cloud have different net radiative cooling effects. And this pattern of the clouds kind of correlates well with two large-scale environmental parameters, which is the inversion strength showing on the x-axis and the surface wind speed showing on the the y-axis. There are still quite a bit of scatter around this four cluster, so we kind of wonder if mesoscale variability play any role in the trade cumulus generation and organization. And specifically, we are thinking about the mesoscale SST spatial variability. The atomic field campaign kind of provided us a good opportunity to look into these questions because it targets the ocean-atmosphere mesoscale interaction. The campaign took place from January 9 to February 12 in 2020, and there were a lot of platforms sampling the ocean and atmospheric properties in the trade wind alley east of Barbados here. In other regions, like in the extratropical regions, previous study have already found that mesoscale ocean eddies, they can modulate surface wind and cloudiness. Shown here is a paper from the Gulf Stream where they composited 400 warm core eddies and show that over the background wind blow over the SST warm core eddies, the surface wind speed is enhanced over the warm core. And associated with this enhanced surface wind speed, there is local convergence anomalies at the downwind edge of the SST warm core eddies. And associated with this surface convergence, you see enhanced cloudiness. Similar imprints have also been found in the Southern Ocean eddies on both winds, clouds, and rainfall. And it's nicely summarized by this paper here. So here you see the same signature again on the wind speed. And for the cloud and rainfall, it occurs slightly more in phase with the SST compared to in the Gulf Stream region. So they nicely draw this diagram explaining what's going on. There is this enhanced cloudiness over the warm core eddies and enhanced rainfall due to this enhanced turbulence over the warm patch here. But then for the region that we are looking at, the atomic region, which is this orange box on these two maps here, in this area we don't really have a large SST variation as in the Gulf Stream and in the Southern Ocean eddies. So on this map on the left, the blue and red color dots are kind of mapping, pointing out where you have 2 Kelvin SST change within a 100 by 100 kilometer region. And then on the right is just showing you where there are persistent SST fronts in the winter seasons. And as you can see, the atomic region doesn't have a strong SST anomalies in the mesoscale and also don't have persistent SST fronts in the winter. And similarly, the in situ measurements during atomic also didn't find large SST anomalies at mesoscale. What we observe is that the SST spatial anomaly is within 0.7 degree, and on average is around a quarter degree. And the scale of this variation is between 30 to 100 kilometers. So the question is, does weak mesoscale and even finer SST spatial variability really matter for the trade cumulus? So I found this paper by Joanne Malkus, who's one of the pioneers studying trade cumulus, and this paper was published in 1957, and she used some aircraft observations and suggests that the presence of trade cumulus clouds are often associated with SST gradients. So in this historical paper, she showed different cases. I'm just pulling out 2. One is in a very weak wind condition, like 3.5 meters per second. She observed that there are some small cloud group forming over and slightly downwind of this 0.16 degree SST jump, and the size of this SST anomaly is about 8 kilometers. And then there's another case where she found when the wind is much stronger, up to 40 meters per second, she also observed similar behavior of the clouds over a quarter degree SST jump. And the size here is about 5 kilometers. So this gave me some hope to find the potential response in this area. So part one of the talk will be me searching for the potential cloud response with satellite observation during atomic using the same composite analysis method in the Gulf Stream and in the Southern Ocean. So first, we use the atomic in situ measurements to validate some satellite data. Showing here is the showing here in red is the hourly SST retrieval from GOES 16, a geostationary satellite. And in black is the in situ measurement of seawater temperature. And then you can see that the matchup is pretty good, and the satellite can capture the in situ SST variability reasonably well. You can zoom in on a particular day, like the first day of the campaign. The ship sampled 2 SST bumps, and this is also captured well by this level 3 SST retrieval. You may notice there are some gap in the retrieval. That's because level 3 product, there's the cloud influence on this level 3 product. So when there is a cloud, you cannot really accurately retrieve the SST. So there is cloud mask in place. So instead of directly using this level 3 SST retrieval in our analysis later on, we use this validation to help us to choose a level 4 SST analysis product to conduct the composite. So we are choosing this ghost post blended SST analysis where this particular level 3 SST source has been injected to create this gridded product. And then we also look at the daily mean satellite cloud fraction and how it compared to the in situ cloud fraction measurement. So showing here, the red markers are the daily mean cloud fractions derived from a satellite. And then the black is the in situ measured cloud fraction from a ceilometer measurement. So this quantity doesn't match up with in situ measurement as well as the SST, but still it captured the day-to-day variability decently. So now we can use the chosen level 4 SST product to locate the daily SST anomalous features in this region by applying spatial high-pass filter at 300 kilometers. The result is showing on the left in this movie. As you can see, there are ubiquitous SST kind of variability in this region, and then it kind of vary from one day to another. The large-scale background SST is kind of shown in here with the blue dashed line. Here, the main feature, main anomaly magnitudes for these SST features are close to 1/4 degree. And the equivalent size of these blobs are about 60 kilometers in radius. These SST features experience 8 meters per second near surface wind speed, and the wind is coming from east to northeast. So, this, features identified here basically provide me some composite locations to extract other atmospheric fields from satellite products, and I can also do this from Arrow 5. So I will mainly show total cloud fraction and 10-meter neutral wind speed. So to composite all the information onto these irregularly shaped objects, I need to have a common composite coordinate, and I'm adopting the same coordinate from the Park et al. Study in the Gulf Stream. So basically, I first approximate the SST feature with an ellipse, and then I do the coordinate transformation, so then we can arrive at this natural coordinate system where the x-axis will be aligned with the background wind, and then the crosswind direction will be on the y-axis. And then I normalize the coordinate by the radii of this SST feature. Okay, so, and then here is just showing the composite results for the clouds. So now I have this nice looking circular SST patch, and then on top of it, the black dotted line is kind of marking the edge of the SST feature. And so you see that in the satellite cloud fraction anomaly field, there is a statistically significant enhancement of cloudiness over the SST1 patch. And although the absolute magnitude looks really small, it accounts for about 4%. It's 4% relative to the background mean cloud fraction here. and it accounts for 15% of the small-scale spatial variability. And again, we can look at the wind speed, and similarly, the wind speed is also enhanced as in other regions, but also, the magnitude is really tiny because the perturbation magnitude is tiny. If we look at the wind convergence, the signal becomes a little bit less, or is insignificant. It didn't pass the 90% field significance test. Okay, so we can look at the same thing in error 5. So error 5 have similar response in the surface wind speed, but the cloud fraction anomaly is a lot weaker and is not statistically significant. Maybe it's not a surprise since the cloud fraction is only a parameterized field in error 5 and didn't really inject any observations. For the error 5 convergence, it passed the statistical significant test. And so what you see here is convergence anomalies is located downwind of the SST1 patch. So basically, this gives me more confidence that in the satellite composite field, the convergence is also on the downwind edge, and this convergence is offset from the enhanced cloud fraction. We also check the error 5 surface fluxes, and both the sensible heat flux, latent heat flux, and the upward buoyancy flux are enhanced locally above the SST1 patch. And this result is qualitatively consistent with in situ observations from the field campaign in both Eureka and Atomic. Okay, so now we kind of wonder the potential mechanism linking the anomalies that we see in SST, in surface wind, and in cloud. So in the literature, it is often shown that cloudiness anomalies being co-located with surface convergence anomalies. And this is actually quite intuitive for us, right? And when you have a low-level surface convergence, it helps to transport moisture upward and then helps to form a cloud. And I further kind of divided this into two groups based on how the low-level convergence anomalies are generated. So first, it can be generated via this hydrostatic pressure adjustment, which create this horizontal pressure gradient and leading to convergence. And several studies have shown this mechanism being active, and it's usually happening on longer time scale and larger spatial scales. There's also another mechanism that can create low-level convergence, and that is associated with this vertical momentum mixing of higher momentum aloft down to the surface. With this mechanism, the convergence will be generated at the downwind edge of the SST1 patch. And so now even though the cloud is co-located with the convergence anomaly, it's offset from the SST anomaly. But neither of these scenarios match the result that I just showed you. So the result we have here is that the cloudiness anomalies is sitting over the SST1 patch, but it's offset from the surface convergence anomalies. And if you do remember, I showed this similar result from the Southern Ocean eddies at the beginning. And so in their paper, they proposed this turbulence and surface flux-driven mechanism to explain this particular pattern here. So I guess we can hypothesize that the mechanism linking the SST1 anomalies and the enhanced cloudiness in the atomic region will be that the turbulence is enhanced over the SST1 patch, leading to an enhanced mixed layer height, as also depicted in this diagram from the Southern Ocean eddy paper. And when the mixed layer height exceeds LCL, then the water vapor can condense and lead to cloud formation, which is pretty straightforward mechanism that others understand well. But we can only go so far with observations. So we wanted to further understand this composite result and interpret them with large eddy simulations. And so here we turn to this System for Atmospheric Modeling, or SAM, to conduct some idealized cloud resolving simulations. So here is our experiment design. So we are running this cloud resolving LES in a 100 by 100 kilometer domain. The vertical extent of the domain is 10 kilometers. We use 100-meter resolution for horizontal mesh, and then 40 meters for the vertical, up to 4 kilometers. And then above that, the resolution is, above that is a stretching grid. And we have 2 sets of experiments. In the control experiment, we prescribe uniform SST, about 26.3 degrees Celsius. And then in the perturbation experiment, we prescribe a 25-kilometer wide SST warm patch. The cross-section of this SST warm patch is showing in this lower panel. And it's a reasonable idealization of the SST warm patch in the satellite composite, which is shown in this dotted, in the dashed line. We also prescribe this SST warm patch at different locations. It's like a burner, and then you turn it on individually in different sets of experiments. And that will create like 4 ensemble members for my simulations here. Yeah, and when I prescribe this SST warm patch, I also preserve the domain mean SST as in the control run. So for the forcing, I use the constant large-scale forcing from error 5 that represents the 2-month mean condition during atomic. I don't have any diurnal cycle in the simulation. I'm using diurnally averaged radiation forcing. And then for the surface, I'm using interactive surface fluxes, but there's no interactive ocean, so the SST anomaly doesn't really vary in time. And also I nudge the large domain wind profile every 6 hours. And for the boundary condition, it's very typical AA periodic for the lateral boundary condition, and then at the top is a sponge layer. So first I need to spin up the model. So I spin up the uniform SST simulation for 24 hours. As you can see, this plot on the top panel is showing the integrated TKE for the subcloud layer showing in black and the cloud layer showing in orange. So the subcloud layer reaches steady state after about 12 hours of spin up. And then the cloud layer is slowly evolving. We sample 4 states of the cloud layers to hot start the 2 groups of experiments, and we pick hour 12, 16, 20, and 24th. And these states, they differ mainly in the inversion height. As you can see in the second panel, the inversion height is increasing with time. And also the shallow cumulus aggregation, the degree of shallow cumulus aggregation. You can directly see them in the lower panel with the cloud water path field. And it's also, the signal is also there in the total water variance in the shaded color. And then, so with these 4 reinitialization states and the 4 location of the SST warm patch, I basically have 16 ensemble members. And then I run the simulation for 6 hours for these 2 groups of experiment when I hot started them. The domain means properties between these 2 groups are pretty similar. For those who are interested, or for context, this stability parameter is 9.4, is in this convective regime. And then the air is 1 Kelvin cooler than the SST. So I will be presenting results in the same analysis framework as in the satellite composite. So showing here is surface air temperature anomaly field. So on the left is this output coordinate in SEM. So what you see is as the background wind is blowing from right to left, the air, I guess the air in the LES can feel the influence of SST warm patch, and then there is this hot temperature plume being evacted by the background wind downstream. And at some point, it recirculates back, but at a different location in the Y because of the doubly periodic boundary condition, and also because my wind is tilted. And then I do the coordinate transformation, and eventually we are only going to look at the result in this normalized natural coordinate. And again, what you see here at 2 is a result of the doubly periodic boundary condition, and I'm not going to talk about that. So in some of the analysis, I'm only going to show you information in the crosswind direction, and this will be just averaging the result across in a crosswind direction between -1 to 1. And also, I will be referring a lot to this response, using the word response a lot, and this basically just means the difference between the warm perturbation and the control run and the ensemble average of that. So first is we want to look at if LES can reproduce the satellite composite field. Showing here is the result from the LES. You can see that they have qualitatively similar structure. The main difference, the first main difference is that the response in the LES kind of shifted downwind by about a radius of the SST warm patch. And this is a result of the size of the SST warm spot. And when we double the size of this SST warm patch, you can see the response kind of shifted more upwind and is now completely within the SST warm blob. But then this experiment is just too expensive to run because now I have to double my domain size. So for the talk, I will just return to the results with the smaller warm spots. Another difference that you can see is that the phase of the cloud fraction is now sitting in between the wind speed and the wind convergence anomaly instead of completely in phase with the enhanced wind speed. So we can look at this in details by looking at the vertical structure of the cumulative cloud fraction response here. Showing here is the vertical slice of this field. You can see the surface buoyancy flux is enhanced in the subcloud layer. And if I take this response at different vertical levels and normalize it by its peak magnitude, then I have this normalized response showing in the middle panel, and the dashed black line kind of tells you how the phase changed with height. And so the cumulative cloud fraction response is more in phase with the SST anomaly below 780 meters, and the phase doesn't change much above that. So now if we look at this cumulative cloud fraction response at this particular height, you see that the cloud anomaly signal shifted upwind and become more aligned with the enhanced surface wind signal. So this is qualitative, consistent with the satellite composite. So we can further look at the vertical distribution of this level by level cloud fraction by looking level by level cloud fraction because the cumulative cloud fraction is computed from this quantity. And again, you see there's very weak signal in the control run, and in the perturbation run, you have this enhanced cloud fraction concentrated within, between the cloud base and 1 kilometers. So now I'm just trying to use LES to interpret the enhanced cloud fraction, the enhanced cloudiness in the satellite composite. So what I did is I take the cloud response and average them within the SST warm patch and outside the SST warm patch. So outside is shown in gray. The shaded area represents the standard error of the mean. So outside of the SST warm patch, you can see the cloud response is nearly 0 at all levels. But then inside SST warm patch, you see the cloud response kind of peak somewhere around above LCL, and then it decays with height. I also plotted the dashed line is the response at the different location where I prescribed the SST warm anomalies. And you can see that the response happens quite consistently at low level, maybe up to 1,500 meters. And then above that, the response becomes more sensitive to where I put the SST warm spots. So this basically suggests that in the real world, when I composite those SST anomalies at different locations, the response in the upper level will likely be canceled out due to variation in the inversion height, in the degree of shallow cumulus aggregation. But what will be left will be this consistent response near cloud base. And so the result here suggests that the enhanced cloudiness in the satellite composite is a signal of the near cloud base cloud response to the SST warm perturbation. Now we want to understand further what caused this near cloud base cloud response. Plotted here is the mesoscale secondary circulation induced by the SST warm patch in panel B, and panel C just shows you the difference between the perturbation and the control run. So now you see this upward rising motion associated with this secondary mesoscale circulation. But the location of this maximum upward motion is kind of offset from the core of the cloud fraction response. But if we look at this vertical velocity variance, which is plotted as contours, you can see this field kind of directly connected to this enhanced cloud fraction, supporting a turbulent-driven cloud generation mechanism. But how exactly does this enhanced turbulence increase low-level cloud fraction? Here we can check if the mixed layer height is indeed above LCL for the above the SST1 patch. And this result here basically suggests so. So on the right is the difference between the mixed layer height and LCL on average in the simulations. I will skip some of the details. But since we are using LES, we can really look further into the more turbulent field. So there are some historical notions noting that the thermals are the invisible roots for this trait cumulus cloud. And once thermals rise above LCL, they can help to form the cloud. So here we are trying to look for these thermals in our LES simulations using the upper several percentile of vertical velocity. And I'm choosing 3% because that's what people have chosen in the past. So when I look at this field in the control experiment and the perturbation experiment here, you can clearly see a signal in the mixed layer where this upper 3 percentile of vertical velocity is enhanced. This is just summarizing the same thing with the red and black line, but this is the average result in the mixed layer. So you can see the peak of this quantity is around where the cloud fraction response peak, which is shown in this gray dashed line. And also this enhanced updraft velocity over the SST1 patch can help to shorten the travel time of the surface parcel with moisture to LCL, as some recent study pointed out. And I think this updraft velocity also helped to quantify things a little bit better because the response here is about 0.1 meters per second. And if I look at the response of the vertical, the mesoscale vertical motion, which is showing in the blue dashed line, the magnitude is about 0.1 centimeters per second. So there's a 2 magnitude of difference. And this kind of explains why the turbulence are more effective in creating clouds than the vertical motions. I think I'm running out of time, so I will just skip this part. But to conclude, the satellite observations and idealized LES converged.
You actually have plenty of time left. You have 15 minutes.
Oh, okay.
Yeah.
Sorry. I was looking at this and it's already 50.
Oh, no. Yeah, it's actually only 2:35.
Okay. So next is we wanted to know how the locally enhanced surface sensible and latent heat fluxes play into this turbulence story. I'm skipping some information here because this is still work in progress. But since we know that from the previous slide, this updraft velocity is connected tightly to the surface buoyancy flux, which is enhanced over the SST1 patch. So we can explain this question a little bit further by doing some homogenizing mechanism denial experiment. But first, let me summarize what is happening in this standard run where my sensible heat flux, surface sensible heat flux, and surface latent heat flux both respond to the prescribed SST1 patch. And we will start from this panel here showing the relative change of buoyancy flux, normalized by the buoyancy flux in the control run. So what you see here is that the surface buoyancy flux is increased over the SST1 patch by about 15%. And this enhanced surface buoyancy flux will lead to a stronger turbulent updraft, which kind of increased the cloud fraction by about 10% over the one patch. And then associated with this turbulent updraft velocity, it also enhanced the entrainment or mixing in the entrainment zone so that it mixed down the higher momentum, temperature, and drier air to the surface. So this is showing the enhanced entrainment in momentum flux, temperature flux, and humidity flux. And so as a result, you see an enhanced surface wind speed, an enhanced mixed layer average temperature, and a reduced mixed layer average humidity. Now we can homogenize the surface latent heat flux response at every time step, but we retain the sensible heat flux response. As you expect, the buoyancy flux response slightly reduced, and from the magnitude of reduction, we can see that the sensible heat flux contribute to about 80% of the locally increased surface buoyancy flux over the warm patch. And because the buoyancy flux is reduced, as you would expect, the entrainment mixing is also, the intensity of the entrainment mixing is also reduced. And as a result, the cloud fraction is reduced, compared to this standard run. And then the surface wind speed response is reduced, and as well, and in temperature as well. But one thing is that the mixed layer humidity is actually getting more dry. And this is kind of hinting at the moistening effect of the surface latent heat flux. We can actually see this by now homogenizing the sensible heat flux, but retaining the latent heat flux response. Now the buoyancy flux is reduced much more because the latent heat flux only contribute about 60% to the surface buoyancy flux. In the same argument, the entrainment flux is reduced, but you somehow see that more clearly in the temperature and humidity. And then you also see this, the mixed layer temperature is, because of the less entrainment of dry and warm air, the mixed layer temperature response is reduced. But now you have enhanced moisture in the mixed layer, and this is because of the reduced entrainment of the drier air from aloft. Now the moistening effect of latent heat flux can actually manifest because it brings the drying process, and so that's why you see this enhancement of boundary layer humidity. So to conclude, the satellite observations and idealized LES converge to show that the trade cumulus cloud can indeed respond to even a few tenths of degree of SST variation in the atomic region. And our LES result further shows that this cumulus response consistently peak at low level, slightly above the LCL, and then it decays with height. Our results also support this turbulence-driven mechanism and to explain the enhanced low-level cloud fraction over the SST warm spot. And so at last, the enhanced low-level cloud fraction is a result of both locally enhanced surface-sensible and latent heat fluxes. The surface-sensible heat flux plays a dominant role in generating enhanced buoyancy flux, which provide a TKE source to increase the strength of the turbulence. And then the enhanced latent heat flux will reduce entrainment drying by replenishing moisture from the ocean. So with that, I will end this talk, and I'm happy to take questions. Thank you.
Okay, do we have some questions in the room?
In your observational data, did you have any measurements of ocean current? I was wondering if you get like ocean eddies that correspond to the warm eddies, and follow-on question would be, did you put those in the numerical model simulation as well as the temperature perturbations?
Yeah, there are surface current measurement from the research vessel, but I don't think that we have those at different levels. When I look at the data, I don't see the currents being turned around very clearly. So and also at this region, there are no large eddies, so there are not really circular current flowing around this warm patch. They are more like what Peter Sullivan would call the submesoscale soup. So the large eddy is actually located along the coast of the Southern America. And so this anomalous SST warm patch are a result of that western boundary current, the energy cascade of that western boundary current. So I guess my short answer is these are not warm core eddies, as in the Gulf Stream and in the Southern Ocean, but they are just some kind of features transitioning from mesoscale to submesoscale, and they don't have a turning current, obvious turning current associated with them. So in the simulation that I did here, I don't have currents at the surface. But I think Peter Sullivan did have a simulation with that effect in it.
Thank you, Xuanyu. Very nice talk.
Thanks.
And my question was related to the previous question, and it was about this is a good slide, actually, about the SST anomalies. And are there more, do you know if there's more warm anomalies than cold anomalies? So would it rectify onto more low cloud or less low cloud?
They are about the same, actually.
Okay.
So over the I'm just trying to find my backup slide, actually. I think I have one of these results from the cold anomalies. So these are the number of cold anomalies is about the same as the warm anomalies. So over the cold anomalies, you see the opposite effect of a reduced cloud fraction. So I guess on an average sense, it doesn't change the mean, but then they do play a role in the spatial variance.
Okay, thank you.
Very nice. So I want to understand a little bit more the turbulence mechanisms. One of your conclusions is that turbulence enhances the formation of these clouds. First, I want to ask a technical question. In the simulations that you're doing, you're applying a temperature boundary condition at the lower surface. Is that?
Right.
So that's how you establish the anomaly, is through the temperature boundary condition?
Yes.
Okay, that's what I thought. And then turbulence-driven mechanisms, if I understood what you said correctly, it's having to do with the existence of localized updrafts? That's what you mean by turbulence mechanism?
That's what we have been explored recently, very recently, actually. I feel like this updraft is maybe a more direct way to understand this effect, because I feel like it's this kind of found local jet that can bring surface
I understand
moisture.
that.
Yeah.
So the question that I have then, if that's what you meant by turbulence, then is that updraft associated with the existence of the anomaly, or is that updraft associated with the turbulence structure within the atmospheric boundary layer over the surface water, or is it a mix of the two?
That's a good question. I think because we are using this ensemble approach, so the native turbulence that is already in the control run will be kind of averaged out. So what you see here is associated with the updraft associated with this additional warm patch that I prescribed.
Yeah, because if you have a warm patch, that's going to induce updrafts, right?
Right.
But I can't understand whether that's what you meant by the turbulence contribution or not, because I usually think of the turbulence contribution as within the atmosphere itself.
Okay. Maybe what I should say is the enhanced turbulence intensity here, instead of creating something out of the blue.
Okay, got it. Right, got it. Thanks.
Okay, we have a few questions on Slido. So Kamal Chandrakar asks, what's the timescale associated with ocean eddy-driven sea surface temperature anomalies? Can that be a factor in cloud variability? Or is it too slow that it doesn't matter for the boundary layer turbulence and cloud formation?
For this particular region, the SST warm patch that I show have a decorrelation timescale on average about 5 days. So in this sense, it's still much slower than the variability of the cloud fields, which is about less than a day. I forgot what's the latter part of the question. Sorry.
I think it was just on the general, like how much does this contribute in kind of in a meaningful way to just cloud variability in general in this region?
I don't really know. Maybe it's kind of related to Justin's question. Like it doesn't really change the mean, but it contributes to a little bit of the variance. Maybe the next question to ask is if it really matters for the cloud organization part of the story, because that seems to be a manifestation of the potential impacts, if any. But yeah, I don't know if that's a good answer.
Thanks. The next one says, thanks for a great talk. I'm curious how important you think it is to capture this kind of small-scale SST heterogeneity and atmospheric response in larger-scale climate models. Are there efforts to parameterize this already ongoing?
That's a good question. Well, I guess from my standpoint, maybe we should start considering that a little bit more. I think the study here is really kind of capturing the lower end of the spectrum where the magnitude is quite small. And I think a lot of the studies for mesoscale ASC interaction actually focus on the western boundary current region where you have much larger SST gradient and potentially those will have a stronger impact on the atmosphere. And I think there are a lot of work ongoing to include this in the ASC coupling framework. I mean, in the numerical model, ASC coupled model. In terms of the parameterization, I feel like maybe it's the PBL scheme in the atmospheric model that can be further improved to include this effect. Because as you see, the error 5 cloud fraction is much weaker than the supply observations. So I think it suggests there are still room for improvement in terms of the parameterization to improve the coupling a little bit more.
Okay. Since we still have a little bit of time, I had a couple questions too. Lose my pen. So maybe I was just looking at this wrong, but it looked like from the observations, the cloud fraction response was centered more over the warm patch than in the model.
Right.
So do you have an explanation maybe for that difference?
Yes. I think I went a little bit too fast over there. So our explanation is really the size of the warm patch in our idealized simulations. So here, one kind of represents 12.5 kilometers in my simulations. But then in the observation, the average radius is 60 kilometers. So there's like 5 times difference in scale. So when we double the size of this prescribed warm patch to 25 kilometers, then this response, becomes more in phase with the SST anomaly. And so size, I think, is one thing to explain the difference there. I think as the SST perturbation gets bigger, you have the turbulence will just getting more focus over it. I feel like I still have something, I don't understand why that is the case, but I guess a short answer to your question is really the size that I'm using in the idealized simulation is a little bit too small.
Okay, thanks. And I guess related to that, so in this test, you'd also doubled the domain size. One question I had is when that warm plume wraps around and comes back in, could that have some kind of impact on the mesoscale circulations for what's actually happening on the heat patch? Because it's kind of coming around and it's not, I would say it's in the vicinity of where it is in the heat patch. So I'm wondering, like, did you try an experiment where you doubled the domain size but kept the heat patch size the same?
Yes, I plan to do that, but I still haven't done it. But yes, I plan to check that effect because the doubly periodic kind of makes this simulation less clean, I guess. But yeah, it's in the to-do list. Okay.
Any other?
Oh, I had one more follow-on question, actually. A collaborator of myself called Nicholas Schneider has been looking more in the western boundary currents. But one of the things he finds is a dependence on the scale, and he interprets it in terms of the Rossby number, which has a length scale in it as well, and wind speed. So there's a dependence of how the air-sea interaction works on this Rossby number, which relates to scale and wind speed. So I think it's consistent with this. That's another way to think of it.
Okay, cool.
Okay, if there's no further questions, let's thank the speaker once more.
Thank you.